All right. Well, thanks everyone for spending your lunch here with me. It's kind of awesome. So, talk about design for manufacturing using multi-jet fusion. I'm David Tucker. I'm with HP. I work in our customer market development group. We're really looking at how, the vision of our group, mission of our group is how do you get 3D printing, additive manufacturing into truly manufacturing applications and for products. This is the safe zone. I get it. So, once again, I'm David Tucker. A little bit about myself. I'm a plastics engineer by training, so I have a degree in plastics engineering. I also have a degree in product design. I've sort of converged those two things together to really talk about design and talk about how the handoff between design and manufacturing actually occurs. Worked in the automotive industry, in passenger car, and also worked in the commercial truck industry, really understanding like the difference of volume going from a high volume product to a low volume product. Transitioned over to HP, where I really hit the pinnacle of my injection molding career. I actually was able to release 750 unique plastic parts in a year with a team of 4 people, quite an undertaking, and learned a lot about what it truly is designed for manufacturability and applying a lot of those principles to additive manufacturing, which we'll walk through here. So, okay. So with every presentation I give, I like it to be actionable. I like people to walk away saying, I learned something, I learned it today, I can use it tomorrow. Throughout my career, that's been instrumentally important. You go to a conference, you go listen to people talk, it has to be something that you take away from that you can start using the next day. So when it comes to design and manufacturing, I think there's 2 important points. The first one is, well, how does the technology actually work? So our technology is different than other additive manufacturing technologies. And then the second point is, well, knowing how it works, well, how do you really design for it or unlock the potential of that technology? So first we're going to dig into how does the technology actually work. So our solution has 3 different components. We have a printing station, we have a build unit, and we have a processing station. The printing station prints, right? The build unit is actually the platform at which the powder is transported and collected, and then transferred over to the processing station where it's decaked and it's actually cooled in some scenarios as well. So from the ground up, this product was designed for manufacturing in mind. It's designed for the continuous uptime of the capital equipment that a manufacturer is going to invest in. And the way that this actually occurs is that the build unit is transferred from the printing station to the processing station, and it really leads to this continuous uptime that we're seeing. So you get this, a 10-hour build and a 10-hour cool. The 10-hour cool is with a fast cooling process. So in using natural cooling, there would be longer times, but from an architecture standpoint, you would need just additional build units to exhibit the same exact process of this continuous uptime. So from an architectural standpoint, from the ground up, it's a manufacturing system. The core of this technology lies in our HP's proprietary inkjet heads. Over 30 years of innovation. I'm sure everyone has a 2D printer at home, the same technology. So you open up your printer door and you see a inkjet cartridge that traverses across the page, right? It speeds up, it slows down, deposits crystal clear images. It really, from a physics standpoint, is truly amazing. HP's taking that technology and has scaled it. They basically created print bars that are the width of a page, and they basically shoot the paper underneath them, depositing the image. No moving parts, no moving carriage. For our technology, we basically took those same page-wide print bars, and now we put them on a carriage again, and we shuttle a complete carriage across the powder bed to project an image, print an image actually. So, and how does this actually work? So there's a couple different steps. Very, very, very simple, right? So in this image, we're basically adding a second layer to a part that's already in the process of being printed. The blue represents new powder that's being laid down across the powder bed. The previous gray image represents a fused part that we're basically applying powder on top of. So basically, we roll out powder as the first step. Then we apply agents. So as we were just talking about, we have this page-wide array that goes across the powder bed one time, depositing fusing agents and detailing agents, basically 2 items. And then we apply energy. When we apply this infrared energy, we get absorption inside of the fusing agent, and we get a cooling process with the detailing agent that gives us very crisp edges, fine details, all of these things that make parts aesthetically usable, feelable, good, good tolerance control, good aesthetics. And we have fusion. So that's the fundamentals of the process. It's a layer process. So we have one traversing print head, and then we have an absorption of energy that all occurs on a layer process. So it's not a point process like a lot of other selective laser sintering processes or FDM processors or things like that. So at the end of the day, this is what we're doing. We've laid down an image, we expose it to light, right? We want what we've printed to be above the melt temperature and all the powder surrounding that to be below the melt temperature. We do this by monitoring with an infrared camera the specific melt points of those materials and verifying that yes, we are over those melt points, and that we are getting fusion and molecular entanglement of all the powder. And that's monitored layer by layer by layer, right? So knowing how it works, the next step is, well, how do you actually design with this technology, right? So it's like, how do you actually use it to provide economic benefit to your company? So you look at the product life cycle, right? Or I guess like the development cycle of a product, and you can really interact with additive at multiple phases, right? So we've demonstrated a lot of picking additive for economic reasons, right? A lot of times we're talking about small parts or highly packable parts that provide good break-even points as compared to an alternate technology. But as you step back, you're actually adding and capturing more value of adopting additive if you start thinking about it early on. So as you move back, if we talk about the architecture phase, we can start combining parts together. So in this example here, we've taken 6 different parts in this top one. We've printed threads, right? We've combined all this inside of a part. We did this during the architecture phase, right? We didn't have a part ready to release for manufacturing and say, oh, let's produce it with additive. This was a deliberate design thought out by that engineer during that phase. And I can pass it around for you guys if you want to take a look at it. There you go. So, and then during product definition, you can capture a ton of value. A lot of companies are starting to do this. This is really changing how you're delivering your product, how you're designing your product, personalizing products specifically for users, and this is really the holy grail for any sort of additive application. I think everyone would agree with that. My area of interest and expertise is actually one step back from just economic assessment. Of saying, well, how do you upfront design these parts so that when I go into an additive environment, that I'm locking all the value of those parts during that phase. So to start that, I have a very interesting approach where I take basically manufacturing optimization and I merge that with design optimization. This is the fundamentals, super clear understanding, super easy. But with every manufacturing process, there's a manufacturing space. We all know this. You can model this X, Y, Z, different parameters that are going to define your manufacturing space and what's considered successful. Within this space, we're always going to make good parts and we make bad parts. There's an optimal process somewhere in that space. We can target those optimal processes if we want to spend enough money to find them, hone in on them, and put basically process monitoring around it to make sure that we're exactly in those spots. But then all around this process window, we have failures, and those characterize failures. We can have surface defects, we can have embrittlement, we can have warpage. We have failures all around. My approach to this is saying, well, let's come through and let's eliminate these failures systematically around this process window using design, right? So can we use the design to overcome these failures and then basically create a larger process window and make more good parts and make more profitability for our companies. This is completely the basis of design for manufacturing. So at HP, we have the liberty of looking at our VATS 2D portfolio for 3D print applications. So doing this, we've really developed a two-pillar approach. So how do you optimize value for multi-jet fusion during the design phase, right? So we have two different pillars that we'd like to discuss when we're talking about this additive adoption with our internal engineers. One is printed layer optimization, and the second is packing density optimization. So what is printed layer optimization? So printed layer optimization is I want to reduce my projected area layer per layer, so I'm reducing the variation of my process. So I'm fusing the same thickness of material again and again and again. I'm not having blackout layers where I go from very thin structures to very fat features and a lot of fused material. And what that really does is it increases our process window. Although we have software that goes through and has a closed loop process for monitoring melt temperatures, if we can account in the design for these elements, though that software doesn't have to react as fast, and we can basically get a lot larger process window and make more good parts. The second perspective, or the second level layer that I would like to exploit is packing density optimization. The key to additive manufacturing for production, economic-wise, is packing density. The more parts that you can fit inside of a build during a process, the better economic output that you're going to get. So what we end up doing is trying to put as many parts inside of that space as possible. Normally, these are done in homogeneous builds, like we see here. One continuous part again and again and again. We started really thinking about that and saying, is that really the best solution for what we want to do? We have a flexible manufacturing platform. We can make anything, right? So how do we exploit the design so that we can actually do that? So if we take a look at what are we trying to get out of manufacturing in general, right? And look at these factors, then design this packing around exploiting these. That's the ultimate goal. So we want to have balanced capacity. We want to have a flexible manufacturing platform. We want to have limited fixed cost investment. We don't want to buy more machines than we have to, essentially, right? We want to have schedule flexibility. We want to have scalability, minimal waste, and I want the parts when I order them. I don't want to have excess inventory of parts. So internally, as we started thinking about this, we started saying, well, multi-jet fusion can accomplish these things, and how can we do that? So we looked at what we started calling a Kanban method of all of our parts. And actually, I was at there was a presentation over in the theater just yesterday where it was a liquid planner in P3, and I talked about digitization, or involves the vision is using Kanban systems. So it really internalized for me as this is something that we actually talk about. I mean, our goal is digitization of our inventory, and basically having a pull system where we make things only when they're actually needed. So we took all of our parts and we said, well, let's put them in these scalable arrays, right, where we have really great build density and we can duplicate those. So as we need more products, we just print more of these Kanban sets. We're calling them a Kanban layer. So we have this reproducible set. And so how do we do that, right? Well, we took all of our parts that are in our printer, and we said, well, let's take those, and then when we need one printer, let's print one Kanban layer, and when we need 3 printers, we'll print a complete build. So this is kind of our goal, our vision for what we were trying to accomplish when we started looking at our own manufacturing adoption. So this is the difference. So if you want to make this, our Kanban layer has 80 parts in it, whereas in the alternate scenarios that you see, those are also the same 80 parts, and those are homogeneous builds, completely packed out with singular parts. Obviously, some of those numbers are really high. You see one at 17,000, one at 48. Different varying levels of inventory, good economic decisions to print them that way, but you're creating excess inventory. You're not doing a process just in time. You're creating a lot of waste. So we said, well, let's print them this other way. And if we need 100 units, how many actual builds are we going to be making? So on all of the examples where they're homogeneous, there's some that are less than 100, so we'd be duplicating those prints, those print jobs, creating some extra inventory, some extra management has to go into those. So on one example, we'd have 34 builds. The other one, 90. It's 90 because some of the parts are actually duplicated inside of the Kanban. So we have multiples of some of the components. So when we saw this, we thought, well, this is really interesting. This is flexible manufacturing. This is digitization of our inventory, and this is started ended up being our ultimate goal. Is how do we do that? So we saw that it really creates value because we can start employing these methods during the design phase, and engineers can start actually designing parts in groups, right? So we actually saw parts like this, where you can actually take a part and you can design it for parts to be inside of it, right? And no other manufacturing process can do this kind of manufacturing. So this is something that we thought was really interesting and that we wanted to exploit. So back to our design conversation, right? So when we talk about packing density optimization, what we started talking about is, well, how do you pack a community of parts together that may be controlled with multiple engineers, right? And multiple time, multiple levels of design stability, multiple changes, and how do you do that? How do you get people to start thinking about that? How do you get them to start working together to make sure that the part fits inside the part, or the parts are packable and stackable, right? And what we see as a benefit here is this: ultimately, you're taking that fixed cost of that material, the fixed cost of the machine operation, and you're spreading it across all those parts. So higher build density is better economics, and also no other process can do this other than additive manufacturing. So we like to start with some design recommendations. I don't like to start with design rules, and people talk about design rules. I'd like to say that I've broken a lot of design rules. So we'll start with recommendations, right? So like, what do we want people to start with? What do we want them to start thinking? So we started saying, well, the first and foremost, identify the build direction when you're actually designing the part. Design with the build direction in mind, right? So we have print accuracy in XY, layer accuracy in Z. Think about that in the design phase. Second, avoid sudden changes in printed area. So this is printed area layer per layer. So as you're building a part, if you think about slicing it, right? Sometimes you're going to be printing just lines and rings, right? Other times you're going to be printing blackout areas. Think about getting rid of those blackout areas after you've chosen your design direction and optimize around that, right? And then think about building density. More parts equals less cost, right? And think about diversity of parts, right? So they all don't have to be the same part. They can be different parts of different sizes. And in the design phase, talk about how do you get parts to fit together. So we have an example here of what we called an injection molded design. I mean, I look at it, and most people look at it and say, oh, that's very much injection molded design. It's got a continuous wall stock. It's got ribs. That's actually a pretty good design. It's got some pass cores. So we started saying, well, let's get rid of those. First, continuous wall stock. Let's get rid of that. Right? We don't need that. That's done in injection molding, right? Because you want to limit your machine tonnage, right? You want to have a cheaper tool. You want to enhance flow. For us, that constraint goes away. So we shouldn't be designing with that constraint. Second, there's some pass cores here, right? A pass core is where a cavity and core shuts off inside of a mold so that the mold can actually open. We don't need those. That's not a constraint anymore. And then third, think about packing density. So we have this part here that used to have a corner on it. And when we got rid of that corner, these parts were able to be manufactured inside of the same space. Whereas before, they would be separated. They'd be like this, right? So that shift in packing density ultimately provides better economics and more justification for actually going to additive manufacturing during the design phase. So there's a lot to take in here. What I'd like to do is I'd like to kind of say, what are some of these guiding principles that when you're talking to an engineer during the design phase, how can you get them to think about additive differently, right? So we have this two-pillar approach. So we started to think about what are ways, like simple ways to more complex, to think about how do you accomplish these goals. So the first one is getting people to think about angles. So when you have a part, traditionally people will take a part and they'll prop it up on an angle and print a part at an angle. And they do that to limit that printed area layer per layer, reduces warpage, increases consistency, right? So get them to think about, well, if you think about that manufacturing space, like do you want tight accuracy on holes and bosses? Well, then print it flat, okay? And second is looking at the surface design. So if you look at this part, which is just a simple cap, and I have it here. Before, this thing had a flat top to it. So as you see us slicing it here, you see on the image on the left, you see just a ring. So as you got to the top, if it was flat, you'd have this blackout surface. You'd have an inconsistent projected area or printed area, layer per layer. So we're saying, well, let's think about surfaces, and let's actually change the surfaces to think about complex surfacing, things like corrugation, and using basically concavity to break up that surface into multiple layers. And then last is looking at the load path design. So looking at like Worf's law, we look at bone growth, saying, well, let's only limit material to where it actually needs to be. And there's lots of topology optimization softwares out there. We've worked with Siemens on limiting, on doing this with one of our parts, but there's lots of softwares out there that people could work with and use. So here's an example where they basically took one of our parts, they devoid it of all the features, they apply loads, the part organically grows where the load's actually being applied, and you get a more optimal design at the end of the day. So the second pillar that we were talking about is how do you increase build density? So build density we see as a very much a key to economics. So the first and foremost, very simple, is stackability. So when you have a part, applying draft to that part so that it can stack and that these parts can be produced in the same manufacturing space shifts economics. If you're not thinking about that during the design phase, you're not going to get economical solutions that'll compete with other technologies. Second is abstraction or a foldable design. So if you take a part, and the 2D industry is based on this on this day. Think about every box that's shipped to us. They're all printed flat and cut flat, and then folded into shapes. Injection molding uses this with living hinges and parts. All right, so it's like you're not actually making things in the folded shape. You make them in a flat, stackable shape, right? That can be manufactured and densified. So we want people to think about, well, how do you do that during the design phase? You want to unlock economics. Being able to produce and densify parts like that unlocks that. And then the last one, and the most important, is communication. So my favorite form of communication is actually going and talking to the engineers that I'm working with and getting them ready for additive manufacturing and talk about these different rules and different solutions. But there's also other tools that different companies can employ to make the process easier. So there's two here that I'd like to show you guys. Well, I guess one actually, the SAP collaboration room, and what that basically is an environment where you basically send your data to your vendors, and you're creating a collaboration room where you're actually documenting all the design for additive manufacturing improvements that you're going to be making on those parts. So you're consolidating all that information so that your manufacturer can give you some information that's gonna help you down the right path. So if you look at this example, the same part that we had showed today, we had used this in collaboration room, basically identifying that we had identified a build direction, identified a design improvement for nestability, which was removing the corner, and then looking at a design rule violation where we're saying, well, let's look at this printed area. If that's not needed, get rid of it. Got an approved design, and then these parts are ready for manufacturing in that phase. So Siemens also makes a packability software, and Autodesk makes a packability software, and lots of other companies too, that you can help start to create groups of parts. So for nesting standpoints, that you get really great nesting outputs. So to pull all this together, we talked about these design for additive manufacturing rules, where we talked about limiting projected area and basically printing parts flat. And then we talked about this Kanban methodology, that we're getting all these benefits of flexible manufacturing platform. At HP, we pulled these things together. So when we pulled these together, we got really interesting results. So basically, we have a before and after shot here. So, and the before shot, we basically took all of our parts that were going to be in a printer, and we said, well, let's create a duplicatable Kanban layer. We use auto nesting software to nest these. Okay, if they needed to be, so we chose the printing orientation, And if they had these blackout areas, we put them on slight angles to break up some of that printed area of variation, right? And then we basically ran an economic model on it. And we got an output of about 487 per part. We can fit 160 of them in there. Got some extra space at the top. Some people have said, well, you can make extra things in there. And my answer to that is always, well, in manufacturing environments, people don't really make extra things. So we need to plan for everything that we're actually going to make. So if it's not planned for, let's not use the space for anything else. But then we said, well, let's employ all of these design rules that we were talking about. So this is one of the parts, right? Where we basically changed it and then put it flat. This is another one of the parts where we designed another part to go inside of here, right? And then we put it inside there, and we created a group. We basically took out all the internal ribs. We created a group of these parts. We had 2 of these. We said, oh, let's add draft of these. Let's add draft of these, and let's make a group of this, right? And then we took all of this and we said, okay, with these optimized designs using the same auto packing software, what density do we get? So we actually ended up getting a better solution. We had a more densified product, right? That more densified product is more parts per build, therefore shifting in economics. So we went from a 487 to about a 420 per part. And this was just the beginning. This was just an exercise to demonstrate, is this a good solution or not, right? And then we ended up saying, well, since we densified this, we can use that extra space up at the top now, right? So that can be part of our scalability approach. And as our demand grows for this product, we can start proving out, basically printing complete builds and complete buckets.
And
that's basically where we're at today. If you have any questions, I'd be more than happy to answer. And you guys, I have some parts if you guys want to look at them and have additional conversations.